Hello, this is Jake, Annika, Charlotte's, and Jacob's Math 54 final project. For our project, we decided to talk about Pascal's triangle. So I'm going to be covering the introduction. So Pascal's triangle is a triangular array that contains many patterns. For example, the sum of each row is equivalent to 2 to the power of n. Here, n is equal to the number of rows. So if we look down here, we have an example. So 1 plus 4 plus 6 plus 4 plus 1 is equal to 16, and 2 to the power of 4, because this row is the fourth row, is equal to 16. Another pattern is if the first number besides 1 in a row is prime, then all of the other numbers will be divisible by it. So we have an example down here. So 7 is the first number in this row besides 1, and 21 is divisible by 7 evenly, so is 35. Again, 35 is divisible by 7. 21 is divisible by 7, and then 7 is of course divisible by itself. So it's been studied by many mathematicians from all over the world in different points in history. Lots of cultures discovered it on their own. And Annika's going to talk about that in a few minutes. The triangle has many applications, mostly in the fields of algebra and probability. And Jake's going to talk about more about the binomial expansion aspect of algebra and probability with counting. So to build Pascal's triangle, you're going to start with zeros in a triangle pattern. So we've got this right here, and then you're going to put a 1 in the middle of the first two zeros, like so. And then you're going to add the numbers together row by row. So 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 2 is 3, 2 plus 1 is 3, and then 1 plus 0 is 1. And I'm sure you get the idea by now. And then you can keep adding onto the triangle in this way. Theoretically, Pascal's triangle is an infinite structure, so you could keep going on forever and ever and ever. Just take a long time to add up. So here's a GIF just showing the same thing that I just went through in real time. And I will pass it on to Annika to talk about the history of the triangle. Thank you.
So just to give a little bit of quick background about Pascal's triangle, it is called Pascal's triangle, but the triangle itself was actually very well known before Pascal came to be. So the first work that historians can trace back to is from an author by the name of Pingala, and that was around 2nd century BC. He published a book called The Staircase of Mount Meru, which you can see in the bottom left corner, and that just included a very simple explanation of the triangle, not really about its properties or anything, but just the triangle itself. Years later, a much more detailed explanation of the same rule was given by Halayuda. So those were kind of the two starting triangles of its time. And then around the year 1000, many mathematicians published their own works of the triangle. These were all independent of each other, and they weren't tracing back to other triangles. They were just all their own ideas, but they happened to be the same idea. So in China, the triangle is known as Yang Hui's triangle. In Iran, it's known as Khayyam's triangle. And in Italy, it's known as Tartaglia's triangle. And so, like I said, they're not copies of each other, but rather independent works. So if you were to describe the triangle in China, it would be called Yang Hui's triangle and not Pascal's triangle. In the early 1600s, a man by the name of Blaise Pascal was born. And so Pascal was a French mathematician who was a prodigy, you could say. He first studied a lot of the sciences, natural and physical science, by the time he was around 13. And then by 16, he kind of transferred over to geometry and did a lot of work there. If you know anything about Pascal's line, that is the same Pascal as the triangle. So after that, he moved into more algebra-based studies, and that is where Pascal's triangle came about. So what he did was he pretty much took those original works and a lot of those illustrations and whatnot, and kind of took all the fragments together and consolidated it down into one work. And he collected it and he kind of manipulated it and whatnot. He never took credit for the triangle, nor did he say that he created it or it was his own original idea, but rather he gave credit to a lot of the original mathematicians who did come up with the idea. But what Pascal did do is he added a lot of patterns to the triangle. So he kind of described the diagonal patterns, the patterns by rows and by columns, and all of that kind of stuff. He also defined the numbers by recursion, which is pretty interesting. So he took the triangle itself plus all of his supplementary information and officially published the triangle in 1655. Um, so him and his partner by the name of Pierre, another French man, were kind of just using the triangle by themselves. They were solving a lot of probability questions with the triangle and just doing a lot of their own studies with it. And so it wasn't named anything in particular. And then Pascal in the early 1660s actually abandoned all of his work in mathematics and sciences, and him and his sister joined the extreme Catholic movement that was occurring. And so the church wasn't fond of his work in math and sciences, and so he stopped working on them altogether and even rebuked them and called them blasphemous. Um, but his partner, Pierre, did stick around. He was still working, still doing a lot of the finishing touches of all the work that him and Pascal had started. And so by 1708, Pierre did end up naming the triangle after Pascal and all that he did. And this became the modern name for the triangle that is known in a lot of the West.
Okay, so there are a lot of ways in which Pascal's triangle can be used, and one of those more simple ways is binomial expansion. And for those of you who don't remember what binomial expansion is, which by the way was me before I had to look up for this project, binomial expansion is pretty much just when you ungroup a plus b to the power of n. And so there's a certain formula for that, and it's just a and b, where a starts the power of n and b starts the power of 0. And then in each term, a goes down 1 power and b goes up 1 power until at the very end, b is at the power of n, a is at the power of 0. And with each of these terms, you have a coefficient c. Even if it's just 1, there is a coefficient there. And basically, the coefficients c sub 0 through c sub n can be found by looking at the nth row of Pascal's triangle. And when you are referring to certain rows and columns of Pascal's triangle, you generally consider the ones on the side and on the top as row and column 0. So when you look at the diagram there, the top is row 0, and then you have row 1, and row 2, and row 3, and it's easy to tell because the second number in each row is the row that it is. And an example of this is when you look at a plus b to the power of 5, and as I said before, when you expand it, a at 5 in the first term and b is at 0, or at the powers of 5 and 0, and in the next term a goes down 1 and b goes up 1, but the coefficients in this particular scenario are 1, 5, 10, 10, 5, 1. And if you look at the fifth row of Pascal's triangle, those are exactly those numbers. It's 1, 5, 10, 10, 5, 1. And so that's very useful, especially when you get into like bigger expansions. Instead of using like FOIL or whatever you would use to expand that, you can just look at Pascal's triangle, and that's all you need because you also know exactly what the variables are going to be to the powers of. Another way that it's used that's fairly simple is combinatorics. And once again, combinatorics is that thing that we talked about this semester where it's pretty much counting and you have all those different formulas and you have different ways to, you're trying to find all the different ways to be able to combine different sets of items. And instead of completing the equation n factorial over k factorial, n minus k factorial to evaluate n choose k every single time, you can simply look at the nth row in the kth column. Kind of how this diagram shows here, you have 0, 0 at the top because that's row and column 0. And then as you go down, it just lines up exactly. And an example of this would be 4 choose 2. And instead of evaluating it, which comes out to be 6, you can simply look at row 4, column 2 of Pascal's triangle, which if you look on the last slide is row 1, 2, 3, 4, and then number 2, so 0, 1, 2, column 2, it is exactly 6. And that will work with any area of Pascal's triangle. And since it's infinite, it can be really useful for when you get to bigger numbers. Like 4 choose 2, really not that bad. It's a pretty simple equation to work out. But when you get to something like, say, 25 choose 17, you don't really want to do that by hand. So it's a lot easier if you have Pascal's triangle with you to just look at that number because it doesn't require any actual hard math. And if anything, it would just be addition to be able to get there anyway, even if you didn't have those rows, Pascal's triangle, as long as it's not exponentially large, obviously. Another way that's used is Sierpinski's triangle. And Sierpinski's triangle is a certain fractal, and I'm going to be honest, I don't really know a whole lot about fractals. I'm not sure exactly what they're used for, and I don't. But Sierpinski's triangle can be found in Pascal's triangle. It wasn't. I don't think it was derived from it, but it can be found in it, or at least approximated in it. And it's a certain type called Pascal's triangle mod 2. And basically what that means is you apply mod 2 to every number in Pascal's triangle. And so what it turns out to be is that you only show the odd numbers, because if you think about it, in this diagram here, you see all like 1 is red, and that's because 1 mod 2 is going to be 1, and so is 3 because 3 mod 2 is going to be 1 again, and then that's the way it was going to be for any odd number. But like even numbers like 2 and 4 and 6, they're all going to be mod 2 and 4 and 6. Mod 2 is going to be 0, and so you take the numbers that turn out to be 1, not 0, and you make those a certain like distinguishing color or something like that, and you'll be able to see that it's kind of small here. It's not a big Pascal's triangle, but you can start to see that it's triangles within smaller triangles. And once again, because Pascal's triangle is infinite, this pattern will show no matter how large you get. It'll always be this kind of like increasingly small triangles making up bigger triangles.
So with Christmas coming up, I thought it'd be fitting to demonstrate one of the ways that we can use Pascal's triangle by using the 12 Days of Christmas song. So if you've ever wondered how many gifts are given throughout the entirety of the song, it turns out that we can actually use Pascal's triangle to answer that. And so I made a visualization to walk us through the problem. And so in order to start out, you start building the triangle with a 1. And so then on day 1, we give a partridge in a pear tree. And so throughout the demonstration, I'm going to use 3 different circles to keep track of the important information. So the purple circle will keep track of the day, as well as the number of gifts given, which are the same because that's just the way that the song works. The red circle will keep track specifically of the cumulative number of gifts given on that particular day. And the blue circle will track a running total of the number of gifts given so far. So on day 2, we give 2 turtle doves, and we get the numbers by adding the 2 triangles above. So as you can see here, you just get the 1 and the 1 to make the 2. The 1 and the 2 makes 3, and 1 and 3 makes 4. So on day 3, we give 3 French hens, And so as you can probably tell, our pattern is just going to repeat. And so we're just going to continue to iterate our way down diagonally throughout the triangle. And so on day 4, we have 4 calling birds. Day 5, 5 golden rings. Day 6, 6 geese a laying. 7 swans a swimming. Day 8, 8 maids milking. 9 ladies dancing. 10 lords leaping. 11 pipers piping. And then we give 12 drummers drumming. And so finally we have reached the finish. And so we can look to our blue circle down here to tell that the final number of total gifts given is 364. And so I thought that was just an interesting way and a cool way to demonstrate one of the many ways that Pascal's triangle can be applied. Okay, so something that I find really interesting about Pascal's triangle is the actual rules that are used to construct the triangle are pretty simple, but out of the simplicity, a lot of interesting complex patterns arise. And so just one simple example is it's called the hockey stick pattern. And so essentially if you add up every element in a diagonal row, the sum will be the element directly beneath it. So like here you could see 1 plus 12 is 13, or 1 plus 6 plus 21 plus 56 is 84. And this applies anywhere on Pascal's triangle. So that's just pretty cool. And I'm sure you've all heard of the Fibonacci sequence, but it's a really interesting set of numbers that occurs some places in nature. And so here you can see that from Pascal's triangle, if you go like up to the right diagonally, that's where it occurs. So it's interesting to see just yet another example of a place where the Fibonacci sequence occurs. And here's just some sources, and there's plenty more that we were not able to cover in this presentation. So you should do your own research and check things out. But hopefully you learned something, and thank you.